the two-sample z-test for the population mean. We need two independent random samples of any size. Each population must be normally distributed, and the population variances must be known. In practice, the two-sample z-test is not used that often, as the population variances are usually unknown. If this is the case, then we can use the sample variances and do the two-sample t-test instead. So we start with two populations. They have a mean and a variance each. We take samples, random samples from each, and work out the sample mean for each. And then we use this formula, which gives us our z-test statistic. It's in the formula book on page 12. Example 1, testing for equality of means. Sample A is of size 40 and has a sample mean 3.412. Sample B is of size 50 and has a sample mean 3.307. Both samples come from populations that have a variance of 0.0490, and we're testing for a difference. So H0 and H1, which we can write in this form, which is more useful. In the test statistic formula, we need to work out this value, which in this case will be 0. So putting all of these values into the test statistic formula, and this part here was 0, gives us a test value of 2.24. So a two-tailed test, 5% significance level, which we split. And we can see that our test statistic, 2.24, is greater than 1.96, so we reject H0. And then we've got the conclusion in context. Example 2. Our first sample has a sample size of 50, sample mean of 384, and this is the population standard deviation that the first sample has come from. So we need to square this value to get the variance. And then we've got sample 2, and we're testing for a difference in the mean sales, so a two-tailed test. The 5% significance level will have to be split. And because we know the population standard deviations and variances, we can do a two-sample z-test. And we are assuming that the populations are both normally distributed, and these are independent random samples. So H1, we're testing for a difference, and our hypotheses are more useful in this form, because now we know that the mean of x minus the mean of y is equal to 0. So this value is 0. So our test statistic is minus 2.17, and minus 2.17 is in the rejection region. So our test conclusion in context. And these are the additional factors. Example 3, testing where one mean is greater than the other. So a one-tail test. So our first sample comes from a population with the standard deviation of 10, so this value needs to be squared to get the population variance. And likewise with the second sample, we're given data this time, so we need to work out the mean of each sample, and the sample sizes are for the first one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And we're testing that the mean alkalinity of water in the lower reaches of this river is greater than in the upper reaches. So L is for lower, U is for upper, and it's saying that lower is greater than upper. So we have H0 and H1, which again is more useful in this form. So this value, that equals 0, goes into the formula here. So our test statistic is 2.57. So 1% significance level. And since 2.57 is more than 2.326, we're going to reject H0 and the conclusion in context. Example 4, where one mean is less than the other. So our first sample is of size 100, and the sample mean is 67. The second sample is of size 150, and the sample mean is 60. Both samples come from populations that have a standard deviation of 15, so this value needs to be squared. And we're looking for a decrease, that the mean weight of lead in the soil decreased after the factory closed. So the mean after is less than the mean before. Or we could say that the mean before was greater than the mean after. So we could say this. So after is less than before, or before is greater than after. So taking this to the other side, we have the large value minus the small value to have a positive difference. So in the test statistic formula, this value is 0. Our test value is 3.61. It's greater than 1.6449. So we're going to reject H0 and the conclusion in context. Example 5, where there's a given difference between the means. So the mean of x is 10 more than the mean of y, which can be written like this. And it's a one-tailed test. We want the letters on the left-hand side and the numbers on the right. So our H0 and H1 is written like this. So the mean of x minus the mean of y is 10. So this value, this highlighted value here inside the bracket, will be 10. So 10 goes inside here. Example 6. We have two samples. Sample size 100. And a sample size of 100 for the second sample. The populations both have the same standard deviation, so we need to square this. To work out the means, we need to divide both of these by their respective sample sizes, so we're dividing by 100 each. And we're testing for increased mean yield of more than 0.1, so this value will be used. So the difference in the means is more than 0.1. So this value here, 0.1, goes here. So this time it's not 0. Our test value is 2.09. 2.09 is greater than 1.2816, so we're going to reject H0. And our conclusion in context.